Okay, the problem from page 97 that I did is 3-5. If the mass of the cylinder is 40 kilograms, determine the mass of cylinder A in order to hold the assembly in positions shown. I redrew it as best as I could, right there. And the first step is to draw the free body diagrams of the components. Okay, so the first one I did is ring E. And here we have tension D. Here's ring E on the diagram. Tension D is acting to the left, and tension A is going down, and tension W is acting at a 30-degree angle upwards. This is a 30-degree angle here. And cylinder A, we have tension A acting up and the weight acting down. And cylinder C, we have the weight acting up and the tension acting up and the weight acting down. And the second step is to find the components of the forces, or the direction that the forces is acting in. And for TD, it is acting in the negative x direction here. So you label it negative x, and there's no force in the y direction, so it is 0 here. And for TA, is acting in the negative y direction here. So you say 0, negative y, because there's no x component of TA. And for TW, it is a triangle. So we have to use SOHCAHTOA to determine the forces. And right over here I drew out the triangle. TWY is here, and this is TW. This is TWX. And SOHCAHTOA says, right over here, sine theta, opposite over hypotenuse, and cosine, adjacent over hypotenuse. And that is how you determine these forces. This is the x value, and this is the y. For cylinder A, we can say that TA and WA are the same weight, because the forces have to be same for it to be in equilibrium. And here's cylinder C. We can say that TW equals weight B. And so since they're equal, we can say TW equals 40 kilograms times 9.81 meters per second squared equals 392.4 newtons. We do 392.4 newtons because force equals mass times acceleration. And that's how we get the force acting, the tension. So the next step is to find the equilibrium equations and solve for them. So here for f of x, we put all of the f of x's in a row. So we have negative d, because the sum of f of x has to equal 0. So here's negative d plus tw cosine 30 equals 0. And we do our f of y equation, so ta plus tw sine 30 equals 0. And we know what tw equals, so we can solve for ta right here. We move the ta over to this side, so it becomes positive ta equals 392.4 newtons sine 30. And we plug that into the calculator, we get this value, 196 newtons. And we do the same thing over here. We move the TD over to this side, and it equals 392.4 newtons cosine 30. And we get TD equals 340 newtons. So since TA equals WA from cylinder A right here, we have TA's value. The weight, we can say that the weight is 196 newtons. So the weight of cylinder A is 196 newtons. But we're trying to find the mass of cylinder A, so we have to do the force equation again. So F equals mass times acceleration. We solve for m. So we have our force, 196.2 newtons, divided by 9.81 meters per second squared, equals 20 kilograms. So the mass of cylinder A is 20 kilograms. And the page 111 problem that I did, I tried to draw it the best that I can. It's because it's a 3D problem, but it's kind of hard. But yeah, here it is. Determine the tension developed in ropes A, B, AC, and AD. And here's the rope D, and here's the rope C, and here's the rope B. And the force is acting in the negative Z direction with 600 newtons. The C force is only on the negative x-axis, and the B force is only on the y and x-axis. But the D force is on all the axes. It's on the Z-axis, the x and y axis. So here's our force body diagram. We have TD is going this way, and TC, TB, and the force of 600 newtons is going down. The second step that we have is find the components of each force. So TC is only acting in the negative x direction, so we can just say negative TC and 0, 0, because there's no forces in the y or z direction. And for TB, since it's at an angle, we can look over here, and here is the y. Here's a 30-degree angle. It's 30 degrees. Here is the 60-degree angle that I used, because I just like to use it like that and put it the 60-degree angle like it, just because it's preference. So I just say TB cosine 60 is the x value, or the tension in the x angle, and here is TB sine 60 in the y, because SOHCAHTOA, like I mentioned in the previous example. So, and they're both going in the positive direction. Here's positive y and here's positive x, so they would both be positive. And so TB cosine 60 and TB sine 60, and 0 because there's no z component of this force. And for the rope D, we have to find the unit vector of the force. So we do the center. We find the distance from the center to component D. So here on the x, it's going 1 meter, so positive 1. And here on the y, it's going negative 2 meters, so negative 2. Here on the z, it's going up 2 meters, so we put 2. And to find the unit version of it, we have to divide by the square root of 1 squared plus 2 squared plus 2 squared, which gives us this value, which gives us 1 over 3 TD. And in the y component we have negative 2 over 3 TD, and in the z component we have 2 over 3 TD. And for the force, I just put 0, 0 and negative 600 newtons because that's acting in the negative z direction. And step 3 was the equilibrium equations and solving for the values. So for the f of x, we take all the components in the f of x and add them, and they should equal to 0. So negative TC plus TB cosine 60 here plus 1/3 TD equals 0. And for the y component, we say TB sine 60 minus 2 over 3 TD, because TB sine 60 here and negative 2 over 3 TD. And for the z component, we can actually solve for TD because there's only one unknown in this area. So we move t over to this side and multiply by 3 and divide by 2, and we get TD equals 900. And then we take this TD value that we have and bring it over to the f of y equation because this only has two components and we just solve for TD. So we can plug this back into the equation and solve for TB here. So once we solve for TB, we get 2 over 3 times 900, which is this 900 here, divided by sine 60. And so TB equals 692.8 newtons, and we can round it to 693 newtons. And we have, since we solve for these two unknowns, we can, and there's 3 unknowns in this, and we solve for the 2 unknowns, we can plug the unknowns into this equation and solve for TC. So we move the TC over here and then plug in our values for TB and TD. And once we do that and solve, we get 646.4 newtons, and that rounds to 646 newtons. And that is the forces in AB, AC, and AD. 646 newtons in TC. In TB, there's 693 newtons. And in TD, there's 900 newtons.